our next challenge really was assuming that we might actually win this award, and we had some degree of hope because we thought we put together a pretty good proposal, and we had the funding that you heard about from the state of Michigan to help with the financing of this activity. So we thought we felt pretty good about our prospects, but we also realized that we had a very tight implementation schedule. And one of the things that we needed to accomplish was to plan how we might actually achieve this, as I said, if we were successful in getting the award. So we didn't stop meeting after we wrote the proposal and submitted it. We kept on meeting. And one of the key elements that followed in the early fall of '87, but before we knew we had the award, was a commitment to develop a 3-node test network linking Marriott in Ann Arbor, MCI in the Reston area, and an IBM facility in upstate New York. And it was really that concept that allowed us to successfully implement and bring up the T1, and the test network, that 3-node test network, continued to play a critical role throughout the overall partnership. A third challenge basically was, from a Marriott perspective, to get the necessary staff to meet the requirements that Marriott had. We had a staff originally of about 30 or so odd folks in Marriott, and we had to hire staff to implement our network operations center on a 7-day, 24-hour basis, add staff for informational services, which was part of the solicitation requirement, and ramp up the staff in Hans-Werner's internet group. And so we, over a period of time, wound up hiring about another 30-odd folks to grow to a staff of about 65 or 70 at the early phases of the NSFNET proposal. There are many more things I could say, and don't have time for in terms of our challenges. I would invite you all to read in your handout that came with your registration, the NSFNET final report, because that covers and does a good job describing our project, and as I say, invite you to do that. With that, I'd like to invite Hans-Werner now to share his thoughts.
Can you guys hear me?
Yes, we can.
Okay. Thank you, Eric. I guess you did not expect to share a stage with me in Washington, D.C. now when you hired me almost 25 years ago. I would also like to express my appreciation to the DoD Advanced Research Projects Agency for developing the underlying framework that made the NSFNET and the Internet possible. Special thanks also to Dave Mills for being my mentor on Internet matters at a time when I knew nothing about it. In the mid-1980s, before the NSFNET, access to the Internet was rather limited. At that time, then ARPA Internet was basically authorized only to US or Department of Defense and its contractors. The NSFNET changed this at a time when using the Internet protocol was frowned upon due to a new mandate by the US government towards using OSI protocols instead. The original 56 kilobits per second NSFNET backbone using fuzzball-based LSI-11 nodes became operational in mid-1986 between the 5 new NSF supercomputing centers and the National Center for Atmospheric Research. Those formerly responsible got the links and equipment in place but ran into difficulties making the system work. I stepped in and turned the backbone into a functional state with access via NCAR's University Satellite Network project, and basically ran the backbone from then on until the new T1 network came online in mid-1988. The rather open access nature of the NSFNET and new routing paradigms constituted a challenge for the Internet, which until then was basically a hierarchical structure centered around the ARPANET. With the NSFNET, there were suddenly multiple national backbones with very different administrations and modes of operation. I was the co-principal investigator for the new NSFNET award to Marriott at the University of Michigan. with Eric Aupperle as the project director having Marriott commitments beyond the NSFNet project, responsibility to the system, responsibility to make the system and its architecture work was on my shoulders, with help from many people working on the components. I also had to spend lots of challenging time with the internet community, trying to make them believe in our concepts and that we would make things work, and I had to argue with those who could just not believe that we would be able to make it work at all. We were working hard with Marriott's dedicated staff and our partners IBM and MCI to make the project succeed. There was a lot of new ground to cover. The backbone nodes which IBM built were basically architected from scratch and were really a distributed system of 9 small computers plus various other parts. MCI thought we were pretty crazy wanting unchanneled 1.5 megabit per second T1 links instead of multiplexing them down to 56 kilobit per second voice-like circuits. When we told them that within a few years we needed unchanneled 45 megabits per second DS3 links, they thought we were completely insane. But both IBM and MCI worked with us through all these issues, and we made it all work in time and within NSF's budget. And they were generally excellent project partners and a real pleasure to work with. Let us also not forget that an integral partner, as important as any other one on this project, was the National Science Foundation, as part of the NSFNet cooperative agreement. Steve Wolf and his staff were very involved, continually part of the decision-making process, and pleasant to work with. Beyond the award itself, the National Science Foundation most certainly deserves as much credit as anyone else for the success of the NSFNet. I think a lot of the initial internet explosion was due to NSF's openness for usage of the NSFNet. Suddenly many more people, especially universities, came to the table. A meeting Scott Brim and I had with Pentagon officials resulted in opening up the Internet Engineering Task Force to the NSFNet and beyond. New routing complexities required innovative approaches, resulting in things like the creation of the still in use Border Gateway Protocol, to hold a meshed internet of many autonomous constituents together. All this laid the groundwork for an internet industry to eventually step in, especially around the mid-1990s, to create an all but globally ubiquitous cyber infrastructure that would have a profound worldwide societal impact. By the time I left Marriott and the University of Michigan near the beginning of 1991 to work on research projects at the San Diego Supercomputer Center, we had already made great progress towards upgrading the NSFNet backbone to a 45 megabit per second T3 capability. We had demonstrated this in December 1990 to the NSFNet community, cross-country and across several T3 nodes, another clear success of the partnership. I also continued to work with the National Science Foundation towards new network infrastructure architectures after I left. I certainly did not expect the degree of success NSFNet had and how many people and projects would quickly come to depend on it. But those kind of things are still happening as the internet gets brought towards even more remote areas and to new users. If the underlying concept is sound, like it is for the internet, and it addresses a real need, it should come as no surprise to see heavy growth. In closing, I would like to point out that the internet should not be viewed as a static build it and they will come environment. It is more like a living organism that has to constantly evolve, build new components, replace or abandon old ones, and so on, including always anticipating the need to accommodate new applications, new users, new environments, new technologies, and a seemingly inexhaustible hunger for ubiquity and performance. I'm done.
Yeah, thank you.
Next, we will ask Jessica, you to share some thoughts.
Okay, it's so good to be here to see all the old faces and people we know and relive the good old days. I was the first engineer hired on the team to build this T1 NSFNet, and that was my first job too, fresh out of graduate school from University of Michigan. So I kind of like grow with the project, both professionally and personally. So because we have such a small team to begin with, so I basically did all the aspect of network design and engineering and putting network together. But today I'm going to just emphasize on the routing issue because I'm mainly working on the routing. basically, the first thing we did for the backbone, because we know it's going to be very big scale, so we said, let's still use the model of separating exterior routing information and interior routing information. So in that sense, it makes the troubleshooting easier and also help preserve the integrity of the NSFNet backbone routing. And the second things the new things we did was Yakov at IBM at that time implemented a simplified version of the standard of ISIS protocol. So we used it, actually, that's the first one we used in the T1 NSFNet backbone to do interior routing. And now, of course, that protocol, although it's a more full standard implementation, used basically by all the ISPs, large ISPs in the internet. And the third thing is about the EGP, evolved to BGP, but I'm going to talk about the routing scaling challenge first. Basically, the growth of the NSFNet, we start to crash routers left and right because the routes grow so much. So first of all, we got one day we got this call from a user connected to the NSFNet that he cannot reach certain destinations of ARPANET. Now at that time, NSFNet T1 backbone has a peering with the ARPANET, so still you enable the people connect to both networks to exchange traffic with each other. So we tried to debug the problem, but it seems like everything works just fine. And it turns out it was that the ARPANET routing table, when the routes reached 100, yes, it basically silently and randomly started dropping routes. And of course, some destination, we just cannot be reached because it's not in the routing table. So it got fixed later. And then it was the NSFNet, our NSS node's turn that one day everything crashed. It's just the routing protocol crashed. And we didn't know why. We frantically tried to debug, and we called Yakov, and finally we figured out that it was, again, the routing table causing problem, and we run out of memory allocated for the routing table. So gladly, Yakov seems to work 24 hours a day, just like we did. So he was able to quickly fix the allocation. We restarted with the new route daemon, and it worked. And third thing is that when I tested that Cisco router, AGS, if anybody remember, when I start to flooding NSF's full routing table to the AGS, it crashed. So I reboot the router. I didn't know what was going on. I reboot the router. Good thing is in my test lab, so it didn't impact any user community. So did it again, crashed it again, reboot the router, reduce the routes from the NSF flooding to the AGS. It worked. So I called Cisco. I said, well, it looks like you have a memory problem. And they sent me this thing. A stuffed elephant basically says, well, we really need to redesign our board to put more memory chip on it. So this is a temporary fix because elephant has great memory. So, that's... And then people actually later tell me, you should get a pre-IPO stock option from Cisco instead of this one. So I think this is $1 million elephant, So, okay, because of the routing scaling, we start to see EGP. It was a great protocol then, but then it's become inadequate because it has 3 minutes update. In the old days, everybody knows. So every 3 minutes, it starts to update routes, and then it's, so we have to use BGP to replace that. I don't have running out of time, but we have great stories. Maybe Yakov can tell. He and Kuklaw implemented the first version of BGP. I was in my lab, put it together. The first time it didn't talk, but then I called them and they shipped me a new code in 5 minutes, and it worked magically. So I think Yakov will talk a little bit, but it's, then we have all the regionals switch to BGP from EGP, and this routing protocol is being used widely today. And I also like to talk about CIDR. If you look at this table, at least it's the address allocation history, but it's also reflect the routing table growth, because at the time, if people got the address, usually it ends up in the routing table and in the NSFNET routing table. So if you look at, there's a growth basically in early 90s, and we managed to, I'm running out of the time. I have a lot of stories, but we this committee basically tried to figure out routing and address scaling in the internet, and the NSF routing table, which we double every 10 months, kind of helped us to convince that this is a really urgent issue. So actually, we developed this new protocol called classless interdomain routing, and I happen to be a co-author of it. It is being widely used, and you can see if later, after 93, the kind of assignment and also the routing table kind of become linear instead of exponential. That was because of CIDR. So I'm running out of time, so I like to have my co-panelists get more time to do this. Thank you very much.
Next, we're going to ask Matthew Dobbins to share a few remarks.
Back in 1985, I joined MCI, and in those days, MCI was competing very heavily with AT&T, of course, and had already established itself as a long-distance voice provider, as a telephony company. But MCI was very actively looking to establish itself as a data network provider as well. Very aggressive, very eager, very much a startup company mentality in doing that. So I found myself back in '85 reading the AT&T DDS 56 kilobit manual, trying to figure out what on earth is this digital data service. So not that many months later, we did have a digital data network service up and running, and quickly after that, we responded to the NSFNET solicitation. There was no fiber. That was one of the big challenges and obstacles. In this day and age, fiber is common and everybody has it. No such thing. We were working with single sideband radios and a few digital radios. I'll tell you, digital radios were much, much more stable. The single sideband on the southern route between Dallas and LA needed fine-tuning about 3 times a day. Just to keep the 56 kilobit services running there. So MCI very rapidly built out more digital radio systems. We were very good at that, at putting up the towers, sometimes in the wrong field, actually. There's one documented case where apparently the construction engineer held the map upside down and actually put the tower on the wrong side of the road in the other farmer's meadow. So we had to negotiate the right-of-ways there after construction. That was a tough one. NSFNET, the NSFNET certainly helped MCI, encouraged MCI internally a lot, and drove a lot of the deployment inside MCI to put up a solid, well-performing digital service. So in our response, what we offered was a full T1 service. I think the solicitation really asked for multiple 56 with a few T1 trunks. And one of the reasons that we actually won the bid was because MCI offered a full T1 network. That was such tremendous capacity. We really didn't know what to do with that or how anybody could possibly fill so much. I recall initially we actually split this huge bandwidth of 1.544 million bits into 3 500 kilobit streams that we ingeniously routed in different directions. That didn't last long, though. That was a matter of months before that all got filled up. Another challenge was, as we learned, that the supercomputer centers are not exactly in the major metropolitan areas where telephony companies have their infrastructure built. So we ended up working with local companies, trying to stretch the copper to support 1.5 megabits, or in some cases, building radio systems, radio shots into the campus environment to make that happen. And a lot of creative solutions were deployed there, but to reach the academic communities and supercomputer centers. For me, it was really worlds coming together. I remember very, very cold, snowy days in Ann Arbor where we huddled in a room that was earlier described to me as the slum, a wooden shed, as I recall, where we all got together and felt that we were doing great things. We coordinated our efforts, and truly the computing world, the communications world, the academic world came together. It wasn't just the academic and the commercial. We had very different backgrounds, but the one driving force, we had a concept that we could all rally behind and that we shared, and there was many technical issues, technical problems that as a team we could easily overcome. And at the time, I do recall we had these academic discussions of what all this could mean to society, what it could mean to the world, and the magical things that we were creating here. We were very speculative and living in a dream world, but the amazing thing is that that dream world really came true. For MCI, yes, it did help establish MCI as a quality data service provider and gave MCI a lot of credibility in the marketplace. So MCI met its goals and certainly pointed to NSFNET as a wonderful experience that we continue to support. For me personally, this was just the most amazing, great, exciting thing, wonderful people to work with and a wonderful experience. So thank you to all.
Thank you, Matthew. Now we're going to have the other video stream, Walter Wiebe. So, Walter?
Thank you, Eric. I'm Walter Wiebe and very glad to be here today to kick off the IBM T1 NSFNet segment. Rick Bovie, who was the TCP IP and NSS software lead, and Paul Bosco, who was the manager of the NSFNet development, will follow my remarks. And I must say, what I'm going to do in the next 6 minutes is almost as challenging as what we did for the NSFNet in '87 and '88. Slide 2, please. On this chart, I wanted to summarize the following 84 to 87 joint studies and related projects in academic information systems that were critically important in building the background skills that enabled our IBM team to deliver the T1 NSFNet. There were key partners that I would like to mention by name and thank as we review these activities, but I don't have time today to mention them all. I will name a few and thank them as we mention them. We first met Doug Van Houweling when he was at Carnegie Mellon, and we were focused on campus computing and land-based services. At the University of Wisconsin, we worked with Larry Landweber and his team on the VM TCP IP. At the University of Maryland, we worked with Glenn Rekhter and his team on the DOS TCP IP. We worked with Phil Long and his team on the LAN ASCII gateway. And at Cornell, where we had the Theory Center and the supercomputer joint project, we worked with Dave Lambert, Dick Cogger, Scott Brim, and many other world-class talents. In '86 or late '85, Doug Van Houweling had moved to the University of Michigan, and we established institutional file server joint study with Doug and his team. And other related ASIS projects that also helped us in building the experience and background we needed were projects that Rick Bovie was technical lead in writing the TCP IP stacks for the academic operating system 370, the RT, the Ethernet and token ring communication support. And as you can see, the TCP IP development leaders in the Research One universities were critical to our having the skills we needed prior to the NSFNet opportunity. In April of '87, we announced what we called the Laureate Series that included the following: the VM TCP/IP, DOS TCP/IP, the 8232 channel to LAN product, and the LAN ASCII gateway. All these products were driven by requirements from our research university partners, as well as extensions with our partners from IBM Research that had similar requirements in their computing environments. And throughout these TCP/IP product development activities, we worked with Barry Appelman, Jake Rekhter, and Jordan Becker. Next chart, please. There were many other that I didn't mention, laboratories and IBM development laboratories that we worked with, including Kingston, Poughkeepsie, Tucson, Boca, Raleigh, Fishkill, and we were able to recruit and hire key resources from those development laboratories. Jack Drescher, who's here with me, we were able to attract, and he became our NSFNET Ann Arbor office manager, and he and Tom Stix's group were instrumental in managing the assembly and the depot process for the NSSs. When the NSFNet project solicitation came along in June, it was the ideal next step after our Laureate Series campus computing efforts. And it didn't take Doug Van Houweling very long to convince us this was something we should do together. It took us about 4 weeks or maybe more internal IBM to develop goals, estimates, and internal proposals and secure approval to join the bid development process. And we thank Bob Mazza for his support, courage, and help in securing these proposals. The proposal development was a wild ride. As Eric mentioned, Paul Bosco joined our team just as we began this process. And I remember he and SS2 spent the entire 20, whatever it was, days, 7 days a week in Ann Arbor. And many of us from the IBM team, Barry Appelman, Rick Bovie, myself, there were many people that spent a great deal of time in Ann Arbor throughout that period. It was great teamwork with MCI and Marriott providing most of the resources. Hans-Werner, we worked with closely. We had met Hans earlier, probably in maybe the summer of '86 at a TCP/IP conference. We started development immediately after the proposal and had a simulated backbone running in the Milford lab in October of '87. And of course, we're ecstatic when we got the word that we had won the competition. Tom Stix and Gaithersburg joined our group in fourth quarter of '87, instrumental in helping us build the test network, as well as all the field support plans. And then he and Jack Drescher's team in Ann Arbor, as I mentioned earlier, led what we call the depot assembly and test process for the 3,488 parts that were required to be built into the NSSs before they got deployed at 13 nodes. We went live in July of '88, received kind words from our friends from Farnet. Paul Bosco convinced us that we needed to provide an NSS for the interop in September of '88. We received outstanding marks for our NSF program review. In parallel, we collaborated with Dennis Ferguson as his team when they were building the Canadian network. It was an amazing experience with, I think someone mentioned it was like a perfect storm. All this came together, the collaboration, the joint effort, certainly one of the most significant things I ever worked on in my career at IBM. And with that, I thank everyone, and I'll turn our segment over to Rick Bovie. Rick?
Thanks, Walter. So I'm going to talk about the I'm going to talk a little bit about the nodal switching system. These were the nodes we deployed on the T1 network. In terms of what were the challenges, you know, we really didn't have a good idea what the requirements were. We had no experience in doing anything in the telecom area, and we had 7.5 months to design and deploy a network and get it operational. By the way, this was a statement from the 1987 project solicitation that the NSF put out. They said it is anticipated that over the next 5 years, NSFNet will reach more than 10,000 mathematicians, scientists, and engineers at 200 or more campuses. So they had an idea as to where we were going. We didn't have much of an idea, I don't think, in our group in Milford, Connecticut, but we did know that you know, this was going to be a challenge. This is a picture of what our T1 nodes look like, the T1 nodal switching systems. On this side of the picture here to the left, you can see T1 links connected through the DSU, CSUs to our node. Our node actually was a cluster of IBM RT-PCs. These were the Unix workstations that we had previously developed for the academic world. We were in academic information systems. And these were Berkeley Unix systems, and these, I guess, were the first IBM implementations of Ethernet and TCP/IP and stuff like that. So we connected a bunch of them together on a pair of IBM token rings, which served as the bus in this multiprocessor router. And in some sense, I guess we sort of over-engineered this as we were designing it, but as we soon learned, traffic grew at a very fast rate, and the over-engineering sort of paid off because we just watched those traffic charts go up every month, 20% per month, and you know, we did have a nice flexible and scalable architecture that did allow us to handle this tremendous growth that we saw on the T1 network. This is a picture of what the network looked like around 1990. 13 nodes, those are full T1 links. As Matthew mentioned, we had previously run a slightly different topology with 448 kilobit per second links. You know, and oh, I did want to correct one thing that Eric said. We actually had 4 nodes on the test net: Milford, Connecticut, Yorktown, New York, Reston, Virginia, and Ann Arbor, Michigan. And this is a quote we got from Guy Alms. Thank you, Guy, and the folks at FARNet, when they said, "We have seldom seen a major networking project come off so smoothly, and never one of such magnitude." Now, we also use the same technology in a couple of other networks. IBM, of course, is a worldwide company, and we have IBMers all over the place. So we actually use these routers to build a couple of other networks, including EasyNet in Europe and CANet in Canada. I think I saw Dennis Ferguson before somewhere, and Dennis, of course, was key in our you know, rolling out this technology in CANet. This is a quote on the bottom of this chart that I picked up from this European history of the web, and that reminded me of the date when we first established this T1 link between the US and Europe. In February 1990, this says, the first transatlantic internet link functioning at 1.5 million bits per second was put into service between CERN in Geneva, Switzerland, and Cornell, it says on the east coast of the United States. And this was a key development because this was really the first time we had a very high-speed link, you know, going across the Atlantic Ocean. And you know, CERN was also a very key location, as it turned out. This link came up in 1990, as I mentioned, and it was in 1991 that Tim Berners-Lee at CERN, of course, rolled out the first web servers, and then, of course, a lot of transatlantic cooperation that, you know, really enabled this internet explosion to occur. Let's see, this is a picture of our T3 nodes. So these, in this case, the serial links are 45 megabits per second. And Paul will talk in more detail about some of the work we did in developing these intelligent network adapters, we call them. Although in this case we had changed the basic workstations that were the foundation of this switching equipment, we changed the systems. We added a bunch of new adapters that had some new chips on them. And of course, we changed a lot of software, but it was basically the same architecture. That is, we had one autonomous processor that would do all the routing work, and we had a bunch of other processors that would do the forwarding work. And one nice thing about this architecture, of course, is that we could be forwarding packets like crazy while the routing protocols are figuring out their stuff. And one very nice side effect of that, or one benefit of that, is that if you have disruptions on one link or on one route, it doesn't have to affect, you know, what's going on stable links in the network. So that was very important, we think, also in terms of allowing this internet to grow to these very large numbers that we saw. And as we all know now, you know, this network was able to handle the 50 million users that we saw on the internet in April 1995 and the 50,000 networks that were attached. And of course, these were CIDR networks at this point, so there were many, many more networks than 50,000 that ultimately were addressable through this thing. And of course, this, as we told our IBM management, we far exceeded our goals of 10,000 users on 200 sites. And this is a picture of the T3 network, and we have some nice testimonials that we received at that time as well. This is a quote I found very interesting. You know, what was the biggest surprise about this? This is a quote from Alexis de Tocqueville, and he was a French aristocrat that came here in 1830 to study this brand new country, the United States of America, and see how it worked. And I was interested to see that he had a lot to say about the importance of communication in terms of developing prosperity. And he also talked a lot about the great job they're doing in communications in Michigan. So I thought that was interesting. And you can see on the chart here, he said, "I know but one single means of increasing the prosperity of a people that is infallible in practice, and I believe one can count on in all countries as in all spots. This means is to increase the ease of communications between men." And he mentioned that America, which is the country which has the greatest sum of prosperity that anyone has ever seen, as of 1830, one reason is because they made the greatest efforts, given their age and means, to procure easy communications, and that's something that we see to this day. And then he also said, "In the Michigan forests, there is not a cabin so isolated, not a valley so wild, that it does not receive letters and newspapers at least once a week." And that's in his book, Democracy in America, published in 1835. So long history of communications in Michigan, long history of communications making the world a better place, and I thought you might find that interesting. A more recent quote, this comes from IBM chairman, recently retired Lou Gerstner, and I thought this was a great quote that we might want to keep in mind. He said, "It's clear that the internet is nothing less than the single most powerful tool we have ever seen for driving business, economic, and societal change." So something we can all be proud of, I think. And at this point, I guess I'll turn it over to Paul.
So I continue and build on what Rick said with a few comments relative to the questions. I actually say just personally, again, one of the most fantastic experiences of my life. I came in as somebody with a distributed computing and computational theory background into this group that was hardcore networking, and have forever spent the rest of my life in networking, so it's been fantastic. I think an unwritten challenge, but one of the fantastic things about working with Rick and his team and a number of guys in the room was as many folks in the room know, Rick and I are about as far apart on the political spectrum as you came, and I think represents maybe even in one hallway the sides of the aisles and different people that came together on this kind of a project. So we had quite a blast, and obviously quite successful. So very quickly, reflecting back, tremendous partnering. I think you've heard that together, for many folks. Obviously, a key piece of the theme that runs through this. Time to scale and time to market, something I think we did very uniquely here, and I think will be picked up later. I think one of our challenges was that we were really concurrently bringing new technologies to market, and Rick mentioned very much not just the first generation of technology, but T1 and T3 adapters that we custom built and began to accelerate things. And growth that was really unbelievable. I can remember arguing with a bunch of Bell Labs folks who had derived the maximum growth rate in any mode of collaboration that I think was like 8.3% per year was the baseline phone traffic and debated that at all we could be seeing the numbers we were seeing, which were I think running about 20% per month for a while. So I think, again, there was a tremendous amount of coupling here between the development and actual operationalization that I think to some degree was a great lesson learned. I think the innovation you'll hear more about on our team from Yakov, who will wrap up our piece. But we also set a new standard in standards, and I think that's a big piece of hopefully what we'll talk about over the next 2 days. A very different way of moving with this train that went from probably 178 routes to tens of thousands of routes in a very short period of time. And I think technology transfer that went more, well beyond certainly the member firms here. A lot of us have gone and had very significant careers across companies that weren't in the original set, and include Cisco and Juniper and players that are very fundamental on the vendor side, but also operators like AOL and Comcast. So very, very key, in terms of memories and building on the stuff that the other folks have said. The growth is something I mentioned them, but I think one of the things we ended up having to plan for, if you remember back in time, as we talked about particularly migrating from the first RT cluster forward, there was actually debate. At that time, there was a primary debate about whether IP was really the right protocol, and some of you may remember the pain of of dialogue with DECnet and OSI and more OSI, and then the ATM and our own SNA guys. So we had extraordinary growth, standards, and challenges, and a lot of these challenges taking place again concurrently at the same time. There's a famous yellow pad story about all routes fitting on 2 pieces of paper, I think, that we locked up each night. John Leddy, who's somewhere in the audience, actually asking whether we would have to automate this someday when we hit 500, which is one of the sort of famous quotes. I think the application changes were another sort of interesting memory in terms of the ability for flexibility in these kinds of projects versus predicting the complete future. So we set a path on IP, and eventually IP and Ethernet, but we left an open path on the application side, and that proved to be very important. I think in the early days there was a lot of debate about providing remote access to major national investments in supercomputing. And I think, well, that ended up true, and in the remote places, as Matt said, the collaboration component ended up being the surprising, and remains to this day, I think, one of the surprising elements of what has happened on the internet, moving obviously from sort of remote access to email and FTP, and well beyond the scholars that we thought would initially be the maybe smaller piece of the audience this would impact. So standards very key. I think we've done that. And then I think, also as a measure of any of these projects, a tremendous, tremendous foundation for success. Not just now, as we see the web evolving, and particularly in my current work in space, the web evolving to become a medium that is a platform, ubiquitous across devices, well beyond the PC as we originally visioned, and spreading to handsets and televisions, and video as a form also, and IP truly becoming ubiquitous. So fantastic project, fantastic team with folks from all possible aspects of the technology and political spectrum, and I think to this day remains a program that is a fantastic model to look at and study from. So continuing our part of the dialogue, and Rick has just sort of mentioned, this is our equivalent of the elephant. You got to remember back again at that point in time, and this was not a point in time where each home was buying 1.5 to 8 megabit per second down-speed links. I mean, we were talking about trying to get channelized T1s and then channelized T3s across the entire country for every person there. And so again, several generations of technology, and I think we'll bring this out to view. But the big debate as the traffic grew was, would it continue? We see this really stretch beyond first the supercomputer interconnect, and then the broader audience, and then into the commercial and then consumer. And of course, we bet very heavily that it would be IP, not the other protocols. And then we can move down a path away from commodity devices, although that provided some advantages, and into really applying some distributed thinking. And so this actually ended up being, and having lived, as a number of you guys know, my life at Cisco and Yakov at Juniper, which is another interesting thing to ponder. But this was probably the first time that distributed routing took place and represented an investment in a move towards a whole industry of specialized telecom equipment in the IP space versus just a software-based approach, which really was the trajectory that even we were taking initially, until again it became very clear that the traffic was not going to mitigate, that this sort of 20% that we couldn't convince people was really happening on a monthly basis, and these routes that were doubling at a frequency that Yakov may mention, this ended up being sort of a foundation for an enormous internetworking industry that happened. So great work in our world. Tim Rolfs, who's here, pioneered this on the T1 side. Lou Steinberg, who's somewhere in the audience, and Rich Woundy, and Rick and my team, very much worked this, and a whole bunch of collaborators, John I mentioned, and many others that worked on this as well. So very neat piece of technology. We'll show this as well, and let me turn it over to Yakov, who made it really sort of all glue together and work from a software side.
One of the biggest challenges we had to face in the NSFNET project was the area of routing, and specifically the interdomain routing. In fact, one of the major contributions that NSFNET project made to contemporary internet is in the area of interdomain routing. Specifically, I am talking about development of the border gateway protocol, BGP. BGP actually was designed in January 1989 over lunch. It was designed by myself. I was at IBM Research at the time, and Kirk Lockheed, who was at Cisco. Shortly after it was implemented by both IBM and Cisco, so we had two interoperable implementations. It was deployed on the NSFNET test network, and in summer of 1989, it was published as an RFC. You may notice that BGP has this name, another name known as 3 napkins protocol. So let me explain to you where this name is coming from. As I said, it was designed over lunch, so it was sketched actually on 3 napkins. But shortly after lunch, we realized that napkins may not be the most reliable media to specify implementation of the protocol that's supposed to be run on the NSFNET backbone. So what we've done right after lunch is we copied these napkins into 3 pieces of paper. And here are these 3 pieces of paper. It's the full specification of BGP. There's nothing else to it. It has a finite state machine. It has the format of all the messages. It has all the code points. And you may notice at the end, it even has author's information with emails and phone numbers. If you look at the original design goals, they were actually fairly modest. The main emphasis on the original BGP design was to overcome limitations of EGP2, which at that point was the only interdomain routing protocol in the internet. Specifically, we need to be able to lift restriction on very strict hierarchy that EGP2 imposed on interdomain topology. And being able to lift this restriction turned out to be one of the main factors that enable us to see internet as we know of it today, which is pretty much very distributed, completely uncentralized system. Another thing which we need to solve at that point was to fix the problem caused by IP fragmentation. What we discovered at that point is that carrying control traffic in conjunction with IP fragmentation is pretty deadly to your control plane. So we had to overcome this problem. In terms of scalability, design goals were really modest. All we had to do is to support few thousand of IP version 4 routes, classful routes. Especially by today's standards, you really should realize that they were extremely modest. And we had to replace EGP2 in NSFNET backbone. From the beginning, BGP generated a fair amount of controversy, and so we had to be involved not just with layer 1 to 3, but also with layer 8. And we solved it very simple. We just said that BGP is just a short-term solution, and it will be replaced by a long-term solution which will solve all problems for all people. Well, now let's see where we are today, 18 years later. Well, we managed to go through 4 different versions and numerous extensions, and we still have plenty of controversy. Nevertheless, BGP still remains the sole interdomain routing protocol in the internet. Instead of supporting classful routing, it supports classless interdomain routing, which is certainly one of the major factors that enable internet to scale to the size that we have today. Well, today BGP carries close to 250,000 IPv4 routes. So you see that from few thousand we managed to get to 250,000. That's a very big distance. In addition to supporting IP version 4 routing, BGP4 also supports IP version 6 routing. And last but not least, what we've seen during the evolution of BGP is that its usage been extended and been very successfully extended to applications that are well beyond interdomain routing in the internet. Applications such as 2547 VPNs, applications such as BGP-based virtual private LAN services, and so on and so forth. Based on this, we should be able to observe that BGP as a technology is a widely successful protocol. It's a widely successful protocol for 2 reasons. First of all, it clearly far exceeded its original design goals in terms of scale. As I said, we aimed at few thousand routes. We have today 250,000. But also, it far exceeds its original design goals in terms of purpose, because originally it was aimed just as an interdomain routing protocol for IP version 4 in the internet. And now it supports IP version 4, IP version 6, and a whole bunch of other applications that have nothing to do with interdomain routing. So what lessons did we learn? Well, BGP confirmed one more time well-known paradigm that short-term solutions tend to stay with us for a very long time. Remember, BGP was a short-term solution. 18 years later, we still have it. And of course, long-term solutions tend to never happen. What is important about BGP development is that from the beginning, it was firmly grounded in pragmatisms. So focus was on having good enough solution. We never aimed at perfect solutions. Why? Because it takes forever to develop perfect solutions, and we didn't have time for this. So as I said, it was very pragmatic development. It was focused on solving practical problems, but solving them in real time. In other words, there was a very strong emphasis on engineering. Given the need to solve practical problems in real time, and given the fact that we've seen technology evolving very rapidly, market requirements evolving very rapidly, what we've done with BGP is we designed it in such a way as make it very flexible and extendable, and it's precisely this that enables us to accommodate technical progress in a timely fashion. And last but not least, I think it's either one of the key, or maybe the key factor that made BGP such a successful technology is that its evolution over the last 18 years had been always very tightly coupled with operational experience and the feedback we got from the service providers.
And we're going to wrap up this session with Mark Knopper.
Hi, can you hear me okay? My name is Mark Knopper. I'm at somewhat of a disadvantage because I haven't worked in the networking field for the last few years, and so I can't rattle off the statistics like everyone else seems to be able to do. But I was there, although for this session, it's supposed to be about the T1 network. I actually didn't start working on the NSFNET project until mid-91. I had been at Marriott since 1980, working mainly on the campus network and on the statewide network and doing all this PDP-11 software and network monitoring. So I was really familiar with designing new networks and implementing new networks, fixing broken networks, monitoring the networks, and various forms of Unix system administration and programming. But then in 1991, I was at an IETF meeting in Atlanta, I think it was in August 1991. I got a call from Eric, my boss, in my hotel room, and he said that it was very important that I take on the role of manager of internet engineering at Marriott for the NSFNet group. And that was sort of confusing because I was heavily involved with these other projects. So I thought about it, and then I agreed to do it eventually. It turned out that there were a lot of problems, actually. The next 2.5 years of my life would, I don't want to say would be a living hell, but it was a very turbulent period. It was constant crises. It was sort of like those 20 days of working 18 hours a day, sort of like for 2.5 years. It was an incredible period. So my involvement in NSFNet was as manager of the IE group, Internet Engineering Group at Marriott. The T1 to T3 transition was supposed to have occurred by then, I understood, but really the T3 network was not stable. The cutover couldn't occur because it was crashing. The other things I did eventually was I also worked on later aspects of the NSFNet project, including writing the routing arbiter proposal, and then later I worked on the Chicago NAP at Ameritech. But about this crisis mode, we had numerous constituencies that our group was responsible for. It turned out that I didn't realize what I was taking on, but what I was actually taking on was overall responsibility for the operation and design and engineering of the NSFNet T1 and T3 backbone. Hans-Werner had bailed months ago, and various people had been manager of this group for a while, and then finally Eric took it over himself. But there were a lot of problems with all aspects of the group. The Network Operations Center was fully overwhelmed with all the crashes. There were these things in the T3 network, these events called blacklinks. Some of you remember blacklinks. That was when one of the ENSS or CNSS nodes would just drop one link. And the only way to get that link back was to reboot the node, but that would disrupt all of the traffic. And what would happen is that the traffic during the reboot of this node, which took, I don't know, 5, 10, 15 minutes. The traffic would have to be rerouted to different parts of the network, possibly causing black links on other nodes. So that it was very difficult. You basically had to wait till midnight or 3 in the morning or something like that to do this rebooting. That was just really bad. So one interesting event that happened during my time in this group was that a lot of these problems were narrowed down to one of the revisions of a T3 card, one of the IBM T3 cards. They call it the Hawthorne card. And there was a replacement for the Hawthorne card, which was much better. Somebody maybe will remember what the replacement name was. But when that card was found to be reliable and useful, and we completed the transition and got rid of all the Hawthorne cards, I had a party at my house, and many people came over, and we buried a Hawthorne card in my backyard, and it's still there.
Upside down.
Yes, upside down. That was an incredible event. But anyway, just a couple more points, since I probably only have 1 or 2 minutes remaining. I just wanted to mention some of the constituencies that I felt that our group and our partnership had at the time, that I was responsible for explaining to them what the deal was. They had read in the paper that the T3 network was working and 100% reliable, and we weren't sort of contradicting that until I came on the scene and I said, hey, this is broken. And if you want me to do my job, I'm going to tell everyone that this is broken. So there were the NSFNET regional techs. Those were the technical people at all of the regional networks. The customers basically. There was NSF itself, who we really tried not to give any bad news to, because otherwise they might not give us any more money. There was Marriott's management. There was ANS, which had come on the scene, and we were partly responsible to ANS. There was the NSFNet Executive Committee, which was all the big muckety-mucks, most of whom are here. The IE group. There was the press. I got flamed in the press numerous times for saying that the network was broken, and they translated that into government throws tens of $millions down the tubes. There was the ComPriv and all this other nonsense that was going on. Oh, and not to mention the other government networks, the Department of Energy and NASA Science Internet, and of course, the new commercial networks, PSI and UUNet, and we were responsible sort of to the whole world, and we didn't really understand what that meant, but a lot of people were becoming reliant on this.
So you're saying it really wasn't a network problem?
No, it was everyone's problem. I was telling some people earlier what I was going to say during this talk, and they kept saying, well, whose fault was it? Whose fault was it? IBM's? Was it MCI's? Was it Marriott? Was it ANS? And it wasn't anyone's fault. We just had to fix the problem. And I guess I'd like to say that we sort of lived happily ever after, but it was a really intense time.
I'd like to thank all our panelists, and with that, we conclude this session.